Welcome to the lecture Digital 3D Documentations in Archaeology. In this part of the lecture, we will focus on a fundamental topic that plays a major role in underwater photography. We will deal with image enhancement methods. Here, we see an overview of the topics we want to discuss in this lecture. This should help us later to find the individual topics more quickly. In this lecture, we have the overarching goal of carrying out 3D documentation both above and underwater and creating 3D models. Things work very reliably above water nowadays. Underwater, we have to solve various problems. We will briefly repeat one or another familiar topic and summarize the most important ones, slowly working our way up to the new problems. If we want to carry out videogrammetry underwater, we have the crucial difference that the GPS signal cannot be received underwater. This is because only long waves propagate underwater up to a certain depth, and the frequency spectrum of GPS signals is far too high for this. We have developed a solution in which a buoy receives the GPS signal above water and can derive a rough localization from the relative distance to the submarine. Once we have this localization under control, we can now also carry out automated underwater recordings for 3D reconstructions. What's more, we can also do SLAM again with videogrammetry. In other words, we can construct an underwater map with just a few points and use it to localize ourselves. Here is another example from Lake Mondsee in Austria of what this could look like. However, underwater photography also poses a number of challenges at the image processing level. That's why I'm happy to look at the subject of 3D reconstructions from an image processing perspective today. On the left, we see a very typical effect caused by the incidence of light and the refraction behavior of light on the water surface. Do you know what this effect is called? We thought about compensating for the whole thing by taking night shots with diving lamps. However, the results were not much better than daytime shots. There is also the problem of floating particles and the associated reflections. The good news, however, is that caustics do not play a major role in 3D reconstruction. Can you explain why this is the case? Surely everyone could answer the last question. If we have the goal of 3D reconstruction, then of course we always have to see how many reliable features we can find in the image. We can see very quickly that the more contrast an image has, the more features can be identified in the image. So if we have a blurred image, we will find significantly fewer features. Underwater, we will find that we are generally dealing with blurred images. The image quality here is much poorer than above water, but this is just one of many problems. In addition to localization, working underwater presented us with another major task. Here, for example, we see the Mondsee again, which shimmers so beautifully green and therefore also leads to green 3D underwater models. Dives in the Zwischenahner Meer in Lower Saxony showed us that there is also red water. Underwater photos taken in Veruda in Croatia in the same year were even blue. So it was time to think about how these different watercolors could be identified automatically and how the images could be color matched based on this. I will explain this method in detail in a moment. This brings us to one important topic of this lecture today, because whenever we are dealing with digital images, we have to think about how we store these images and which color space we choose. We are all familiar with the additive RGB color space with the components red, green, and blue, which is used as standard in most programming languages to display colors on the screen. The digital images that we receive via the camera are also typically coded in this color space. Additive now means that the color white results when we use the R, G, and B channels to the maximum. In OpenGL, we specify these channels in the interval from 0 to 1, and in Java, for example, between 0 and 255. In book printing, the subtractive CMYK color space is used, with the color channels cyan, magenta, and yellow for yellow. The letter K stands for the black ink so that we can print with less color. And then we got to know the HSV color space, which receives its colors via the inputs hue, saturation, and value. In order to enable precise, reproducible, and device-independent display of colors, calibrated color systems must be used. These color systems are also referred to as colorimetric. With the CIE-XYZ, we have become acquainted with the mother of all color spaces, which is the basis of practically all current colorimetric color spaces. We were also able to argue that although RGB, CMYK, and HSV are simple color space representations, we understood that they cannot represent all colors and are therefore incomplete. The CIE-XYZ color space is based on three imaginary primary colors, X, Y, and Z, which were chosen so that all visible colors can be described with positive components. The visible colors lie within a three-dimensional region whose shape resembles a sugar loaf. To the right, we see the RGB color cube embedded in this space. If we ignore the brightness, we can represent the possible colors in the CIE chromaticity diagram in 2 dimensions. Using a gamut, for example a triangle for the RGB color space, we can now enter different color spaces. If we select 3 points, for example, we can use barycentric interpolation to display only those points or mixed colors that are located within the triangle. The biggest disadvantage of the original CIE-XYZ color space is that geometric distances in the color space are perceived very differently by the viewer. In the magenta range, we perceive large changes over even short distances, while in the green range, the color tones appear comparatively similar over greater distances. This is where the CIELAB color space comes into play, which was developed with the aim of linearizing color differences in relation to human visual perception and at the same time achieving an intuitive, comprehensible color system. We have already seen the RGB color cube as a distorted cube with straight edges and side planes in CIE-XYZ. If we represent this color space in CIELAB, we obtain a very non-uniform body. The coordinates of the CIELAB color space are the lightness L and the 2 color components A and B. A describes the color position along the green-red axis and B along the blue-yellow axis. All 3 components are relative and refer to the neutral white point of the color system, hence the abbreviation LAB. How do you think color space adjustment is usually done in underwater photography, or what tools would you use to achieve this? If we include a color chart underwater, we can use Photoshop to perform automatic color correction. Photoshop then adjusts the contrast and color by identifying shadows, midtones, and highlights. The default version neutralizes the midtones with a medium gray and crops the shadow and highlight pixels by 0.5%. This is a common method for enhancing underwater images. If we don't have color charts available and want to edit images with low contrast, as in this example from the Mondsee taken with a GoPro Hero 4, the enhanced image provides high contrast areas, but the automatic color correction is not very useful here. We have given a lot of thought to an automatic method that does not require a color chart and can also deal with poor image material. Let's assume that we know the color of water. Then a very well-known and often used equation for the representation of fog or haze by Koschmider, which was established as early as 1924, can help us. J represents the image without fog or haze and A the watercolor. We can understand the parameter T as a weighting between the 2 situations. The image on the left represents the watercolor A, which we obtain with T equals 0. The image on the right is the image J without haze or fog influences. In between, we see the slow transition between the 2 representations as a function of T. Our idea now works in 2 steps. First, we try to determine the watercolor from a set of images in a suitable way. Then we use this color to correct the images and subtract the watercolor from them. This idea was then implemented very successfully in the JEnhancer program. We now have a selection of images available in which we hope that in some places there is a wide view into the water and therefore the watercolor can be found there. We now load the first image and save it in different scaling levels. We have now created a so-called image pyramid. However, as we have not yet dealt with this topic here, we will simply pretend that there is only one pyramid level with the photo. Now we go through the image pixel by pixel and look at the neighboring pixels in a previously defined neighborhood at each point. For example, I have chosen the 8th neighborhood here. We now do this for each color channel. In RGB, this would be the three color channels, red, green, and blue, and in CIELAB, correspondingly, L, A, and B. Now we determine the respective maximum in the area and subtract the minimum from it. This gives us the gradient, the spectrum, or the variance of the values in the range of this pixel. Since we have three color channels, we select the maximum of these three gradients and now have a map with all these values. The pixel with the lowest spectrum is now a potential candidate for our watercolor. Once we have determined a minimum from each of the different images, we then take the smallest of all these images. We have thus determined the watercolor A. The method presented can be carried out either in the RGB color space or in CIELAB. In JEnhancer, we are already using CIELAB here. In the exercise, it is sufficient to use the RGB space. To determine the original color, however, we now only want to use the image pixels in CIELAB. We can also see the advantage of this using the methodology. To do this, I would like to briefly transform the Koshmida equation and look at it in CIELAB. With A and B, we have two color channels available in CIELAB. If we now use the watercolor A as the original vector and assume that J0, J1, and J2 represent three sample pixels in their originally correct original colors, then the real pixels lie on the direction vectors from A to the original colors. The distance then indicates the transmission. Unfortunately, however, neither the original color nor the transmission are known. We can therefore only make estimates here. If we want to estimate the transmission, this now results proportionally from the length ratio of the distance from A to J and A to I. If the transmission is 0, the pixel is equal to the watercolor, and if it is 1, we have no influence of the watercolor. This allows us, for example, to move colors that are very close to the watercolor to the center and leave colors that are unaffected unchanged. If the watercolor is then the new origin of the color space, we can even amplify the color from there without overdriving it. I would like to show the correction step after determining the watercolor here again in an overview. So we have determined the minimum of all variance maxima and no A. We use the transmission to determine the influence of the watercolor on a pixel. I is always the existing image pixel color, and J is the saturated color that results when we start from A and pass through I to the outer area of the sphere. If the transmission is 0, the pixel is equal to the watercolor, and if it is 1, the watercolor has no influence. We then subtract the determined influence of the watercolor from the respective pixels, which results in the watercolor ending up in the center with a medium gray. From there, we can now enhance the color of all pixels without overdriving them. We do not know the original color. Since we also use L as a color channel in CIELAB and treat it as we have already seen with A and B, the image is also significantly enhanced in contrast. This means that, as a side effect, we can extract significantly more features even in poor images, which means that 3D models for blurred underwater video recordings are also possible. Here we see a comparison between three original images with the identified SIFT features and below the respective features through Photoshop and our JEnhancer. Compared to Photoshop, however, the results of the 3D models without the use of color plates are much closer to reality in the end. Improving the underwater images and thus the 3D models then allows us to concentrate on the essentials again. In this case, a shipwreck in Veruda that was uncovered step by step. What do you think could go wrong with the approach presented by JEnhancer? At the beginning, we had made the assumption that the watercolor must be clearly visible somewhere in the pictures. So we look into the distance with the images. If, for example, we take pictures from a pool where visibility is normally very good and we always see the blue border, then the program incorrectly assumes this color to be the watercolor and produces a very strange result. I would like to come back to an important point from earlier. We talked about the fact that the richer the contrast in an image, the more features can be identified. A popular topic is the automatic white balance on digital cameras, which can sometimes lead to bizarre results in practice. Can you imagine why we shouldn't use automatic white balance for underwater photography? During a dive in Lake Mondsee, we can see the shimmering green water in the background. The automatic white balance was switched on here and suddenly the underwater images look bluish. It is particularly important here that we always take the pictures without this automatic white balance, as otherwise our color space transformations will of course no longer work. When you study the properties of water so intensively, the knowledge you gain can sometimes be put to very good use elsewhere. Simulation is very important in robotics. We can simulate robots and environments and generate test data. We also did this for our underwater robot and used the concept from the JEnhancer to degrade the virtual environment accordingly. Here we see a 3D model initially reconstructed from video data, which was artificially degraded again after color correction. If you are interested in looking at other topics in the field of computer graphics and trying out examples in Java, you can now browse through the program collection for my computer graphics book. You will also find a few shader programs for simulating water. One last question for today. What has happened in the field of research since JEnhancer in 2017? In 2019, for example, the see-through method was launched on the market, which, like the JEnhancer, is also based on the dark channel. Normally, there is a cloudy, blurred area in the background where the watercolor is assumed to be. This is slightly different here. This is because RGBD images are used as input, which also determine depth information in real time in addition to the color information. The depth information significantly improves this approach, as the example shows. However, we need special cameras for this. Here we see step by step what happens with the see-through method. On the left we see the raw images with a color plate. These are very green shimmering. Next to it we see the range map with the depth information in column 2, where we can already see that the depth map only works for a certain range. The further the range goes into the distance, the more unclear the situation there becomes. This information is then later removed from the image, which we see as black areas. In the third column we see a simple contrast increase, and in column 4 this is then combined with the dark channel prior method. We can see the removal of the background in column 5, where a significant image reduction is possible and the first watercolor is already estimated here. In the last column we see the result after the correction steps. In 2023, a new method called deep sea color was introduced, which is also based on the RGBD images, but learned and later estimates the levels using a convolutional neural network. This automation is a typical trend in computer vision. Here we still need special hardware to determine the depth information. After listening carefully to this lecture, answering the following comprehension question should help you to summarize the most important statements again on your own. In this practical part, we want to try out the JEnhancer software for ourselves. This is the process and the result with the sample data.